This lesson is on related rates. It basically has to do with trying to figure out how things change and at what rate, and how different things that are related affect each other in the way they change. This will make more sense as we go through, I promise. First, let's imagine that the radius of a circular puddle was increasing at a rate of 2 centimeters per second. So it's raining and we've got a puddle that's growing, and the radius of that puddle is growing at a rate of 2 centimeters per second. When the radius is 8 centimeters, how fast is the area of the circle expanding? Well, first you have to figure out what formula to use, and they're asking us about the area of a circle. So I would do A equals pi r squared. Now they're asking us about the rate, or the rate of change for these things, so we need to take the derivative of it. We're doing it with respect to time, so you can do dA over dt equals, then pi r squared would become 2 pi r, because you multiply by the 2, subtract 1 for the exponent, dr over dt. So that is the derivative of this area formula. So now we look at what they give us. They tell us that the radius is increasing at a rate. So here are the key words: radius, rate, 2 centimeters per second. Since it's the rate for the radius, I know it should go in for dr dt, because that's what dr dt represents. It's how quickly the radius is changing, just like dA dt represents how quickly the area is changing. So dr dt is 2. Now as we keep reading, it says when the radius is 8. So that's just talking about r, the actual radius. Not how quickly it's changing, just the radius itself was 8. Then it says, how fast is the area of the circle expanding? Sorry, I missed a V there. But the area of the circle, the rate at which it's expanding, would be dA over dt. So that's what we're trying to solve for. And now that we've got all the other pieces, we can just multiply it through. 2 times 8 is 16, times 2 is 32. So we get dA over dt equals 32 pi cubic centimeters per second. So again, these terms with d's, the dr dt and the dA dt, are all about rates. They're the rate at which these things are changing. Next example, we have the radius of the ice cream inside of a cone was decreasing at a rate of half a centimeter per minute. The height was decreasing at a rate of 1 centimeter per minute. When the radius was 2 centimeters, the height was 5 centimeters. How quickly was this person losing their ice cream? Well, this equation is given. If you're doing the AP calculus test, then they're going to give you pretty much every volume equation. I think sometimes the circle ones, like I did before, area of a circle or circumference, they assume you know, but any volume equation they always just give you. So we have the volume of a cone here, 1/3 pi r squared h, and to take the derivative of this, it's going to require the product rule, because we have r squared times h. So the derivative of v is just dv dt, but then for the other side we're going to have to use the product rule. So f is going to be 1/3 pi r squared, and g will just be h. F prime will be 2/3 pi r dr over dt, and g prime will be dh over dt. So we get 2/3 pi r h dr dt. That's f prime times g I just did. And you can put those in any order you want, but the order I put them in is what you'd probably typically see in a textbook or something like that. Put the constants or coefficients first, then the variables, then the dr tt at last. Plus f times g prime. That'll be 1/3 pi r squared dh over dt. So that's our entire equation. We had to use the product rule because it was r squared times h. We were multiplying two different variables together. Okay, so now let's start filling this in. If we go back up here and look, it says the radius was decreasing at a rate of half a centimeter per minute. So I know that's the dr dt because it's the rate of change for the radius. I also know I need to make it a negative because it says it's decreasing. So dr dt will be negative 1/2. Now it says the height was decreasing at a rate of 1 centimeter per minute. I know that has to be dh dt because that's the rate at which the height is changing, and it's going to be a negative 1 because it is decreasing. Now it says the radius is 2 centimeters, so that's just r. It's going to be 2. And the height is 5. So I plug in 5 for h. Didn't leave myself a lot of room there. Then it says, how quickly was this person losing their ice cream? Well, if you look, we've actually filled in everything because the rest is just constants. And we're trying to find dv over dt. Now, whether or not you have a calculator, I would always encourage you to just leave things in terms of pi. So I don't have a calculator on me at the moment, so we'll just do this by hand. Negative 1/2 times 2 is negative 1, times 5 is negative 5, times 2/3 we get negative 10/3 pi, plus negative 1 times 2 is negative 2, times 1/3 is negative 2/3 pi. Oh, wait, sorry, I said that wrong. There's a 2 squared right there. Sorry, I'm a little jumbled up there. 2 squared is 4 times negative 1 is negative 4 times 1/3 is negative 4/3 pi. And that's going to give us negative 14/3 pi, and that would be cubic centimeters per minute. That would be our rate of change for how quickly the ice cream was being lost. Okay, next up, we have the volume of a spherical balloon is increasing at a rate of 20 cubic centimeters per second. How fast is the radius increasing if the volume is currently at 36 pi cubic centimeters? Alright, so for this equation, when we take the derivative, we don't have to use the product rule because there's just one variable, r cubed. So I multiply by 3 and get 4 pi r squared dr over dt. Okay, now it says, how fast is the radius increasing? So my goal here is to find dr over dt, meaning I need to plug in something for r and something for dv dt. Well, let's look back at what they gave us. The volume of a spherical balloon is increasing at a rate of 20 cubic centimeters per second. So if you pay attention to units, it gives you a big hint. The only thing that's ever cubed is volume, and it's per second, so it has to be a rate. So 20 is the dv dt. It's the rate at which the volume is changing. Then it says, how fast is the radius increasing if the volume is currently 36 pi cubic centimeters? Well, wait a minute. We need the radius, but they just gave us the volume. So what do? Well, we go back and we look at the original right here. Because if you plug 36 pi in for the volume, then you can solve for the radius. So cancel out the pi's, divide both sides by 4/3, and you'll get 27 equals r cubed, or r equals 3. So now we can plug in 3 for r and solve for dr dt. Okay, 3 squared is 9, times 4 is 36. And then I just divide the 36 pi over. Please, when you do this, make sure the pi stays in the denominator. It can't just magically float out to the side or up top. It's got to be part of the denominator. 20 and 36 both have 4 in common, so we can reduce that to 5 over 9 pi. And that will be, let's see, what was our units? Centimeters per second. That is how quickly the radius is changing. Last example, we have an airplane flying, and we're going to call the distance between the airplane and this building with the satellite on top s. And we're told that the plane also is flying at a constant altitude of 6 miles. So the plane is always 6 miles above the ground. I didn't have that written down, but it's part of the problem. If s, the distance between the nose of the plane and the building where the satellite is decreasing at 400 miles an hour, and s is equal to 10, how fast is the plane flying? Okay, so we've got s equals 10, and we know the rate at which s is changing is 400 miles per hour. Alright, so first let's look at what they're asking. How fast is the plane flying? Well, how fast the plane is flying would have nothing to do with how much this line is changing. That doesn't make sense. You don't measure something's speed based on something on the ground like that. Instead, we want to know how fast it's moving this direction. So what we're actually going to do then is create a right triangle. We have a right triangle here because we want to know, we'll just call this distance x, I guess, why not? We want to know how quickly that's changing because that will tell us how fast the plane is flying. So if you notice, we have a right triangle now. The hypotenuse is 10, and if this side over here is 6, then this side over here is also 6. So we can actually set up the Pythagorean theorem with these because we're dealing with the three sides of a right triangle, so the Pythagorean theorem would make the most sense. So normally the Pythagorean theorem is a squared plus b squared equals c squared, but the way I have this picture labeled, it would make more sense to do 6 squared plus x squared equals s squared because these are my two legs and this is the hypotenuse. Okay, actually let's not put 6 in there, let's just go ahead and call that a and we'll come back and fill that in a little bit. Alright, so when we take the derivative of these, we get 2a dA over dt plus 2x dx over dt equals 2s ds over dt. And the variable we're trying to solve for is dx over dt. That is the speed at which the plane is actually moving because it's the speed at which this distance is changing. Okay, so we are told already that s is equal to 10 and that the rate of change for s is 400 miles an hour. Alright, actually it says decreasing, so we'll put negative 400 there. So if we come back to the front of the problem now, 2a, we know a is 6 miles. That's the distance, that's the height of the triangle. So what about dA dt? How quickly is that changing? Well, if you remember, I said that it's flying at a constant altitude of 6 miles. That means the height of this triangle is not going to change. And if something is not changing, then its rate of change is 0. It's not changing, then its rate of change is 0. So that's actually going to wipe this term out completely. We don't even need it. Okay, so all we need now is to figure out x, and we'll be able to solve this. Well, if you look, I'm just going to redraw this same triangle. We know this is 10, this is x, and this is 6. So we can solve for x by using the Pythagorean theorem. Again, we're going back to our original equation, in this case the Pythagorean theorem, and solving for a variable we need. So if you set this up, 6 squared plus x squared equals 10 squared, and solve for x, you'll find that it is equal to 8. So that's what I will plug in for x. Now it's just a matter of solving for dx over dt. 2 times 8 is 16. 2 times 10 is 20, times negative 400 is negative 8,000. Divide both sides by 16, and I get that the plane speed is negative 500 miles per hour. And all the negatives implying is that the distance between the plane and that building is decreasing. So if you'd rather just put a positive 500 in this case, that would be fine. Because that's really only implying that the distance between the building, because that's our point of reference, and the plane is decreasing.